Okay, so one important thing to know about any kind of computation is how the states evolve, how the computation evolves. And since we know that quantum computation is not deterministic, but all computations are carried under probabilistic laws, um, any quantum computational step is carried by unitary transformations. Okay. So now recall that a quantum bit can be represented by a two-dimensional complex vector. So if psi is a quantum state, let's call the amplitudes alpha 0 and alpha 1. So this means that psi is alpha 0 in the canonical basis. This means alpha 0, 0 plus alpha 1, 1, such that alpha 0 and alpha 1 are complex numbers, and that magnitude square alpha plus magnitude square alpha 1 is equal to 1. Okay, so magnitude square of the amplitudes add up to 1. This is because we want to work in normalized systems. Now, this doesn't mean that the qubit is in state either in state 0 or 1 with these probabilities. It means that it's in the superposition of 0 and 1 with these probabilities. Okay? So unlike a classical probabilistic system, a qubit can be in all basis states, but in a classical probabilistic in classical probabilistic computation, a probabilistic state or a state in probabilistic machine can be in one of the basis states. Okay, but it can't be in all basis states simultaneously. So this is one difference between classical probabilistic systems and quantum systems. Okay, so we want all transformations to be unitary in quantum computing. The first reason is that it turns out that unitary transformations are reversible. Now, remember that a matrix U is unitary if U times adjoint of U equals U adjoint times U equals the identity matrix. So the inverse of a unitary operator U is always its adjoint. Okay? So unitary transformations are reversible. Reversible in the sense that we can always uniquely recover the output from the input. We can always recover the input from the output. Okay, the NOT operation, for example, classical logical NOT operation, the NOT of 0 is 1. And we can recover the input from the output because the NOT of 1 is equal to 0, right? So it's like that. Okay, so we can, in fact, we can verify that given a unitary operator U and a vector V, so we start with V, okay, and we apply some unitary operator to V, okay. And if we apply the adjoint of U, okay, so since U adjoint times U is equal to the identity matrix, what we are left is I times V, and this is equal to V, right? So by applying the inverse of the unitary operator, we get the original input. Okay, so, and second reason for using unitary operators in quantum computation is that they preserve inner products and the norm of the vector. Let's state them in a proposition. So unitary operators preserve inner products. That is, so if U is a unitary matrix, if U is a unitary matrix, then given any vector v and v prime in n-dimensional complex space, we are ensured that the inner product of uv and uv prime is simply equal to the inner product of v and v prime. So this is what we mean by the preservation of the inner product. Okay. So I'm not going to give the proof of the proposition. The proof can be found in the lecture notes. And one consequence of this proposition is that unitary operators preserve norms. That is, the norm of u times v is equal to the norm of v, given any vector v. Okay. Okay. Of course, it's. I think it's best to note that we assume that we're working in a closed system, meaning that we ignore all the environmental effects coming from the environment, coming from outside, so we ignore special relativity. So closed quantum system, meaning that qubits don't interact with each other, okay, in a destructive way, in a way that they interfere with each other, you know, and like break the system apart. So we assume that we're working in an idealized system where everything is perfectly defined and qubits just, you know, evolve in their by their own. Okay. Of course, this is a mathematical assumption, and physically this may not be the case. So that's why we need error correction. Okay. All right. So this is discrete state evolution. Now, in any quantum mechanics course, one learns that the continuous time evolution of a closed quantum system follows the Schrödinger's equation. And we're not going to talk about Schrödinger's equation here. I mean, this is a quantum computation course, not a quantum mechanics course. So we take every state evolution to be to have the discreteness property. Okay, so we're talking about discrete state evolution, not continuous time evolution of quantum systems. Okay, so the next is to consider observables and measurements. So I'll see you in the next video.